Hi, everybody. Welcome to this series for the Research for Industry talk series. I'm pleased to introduce one of my favorite people from the University of Pennsylvania and a former mentor of mine, Andreas Haeberlen. He's an associate professor, and his research interests include distributed systems, networking, security, and privacy. He's recently been working on secure network provenance, accountable distributed systems, and differential privacy. We're so grateful for Andreas to be here, and with that, I'll hand off to Andreas. Oh, I'll actually also note that if you have questions, please put them in chat. At the end of the talk, I will basically pose them to Andreas, and then he'll kindly answer those questions. Thank you.
Sounds great. Thank you so much for having me. Thank you so much for the nice introduction. So what I'm going to talk about is joint work with quite a few people here at Penn who are listed on the slide. So I want to start by telling you a little bit about what I mean by federated analytics. And so, let's think about a concrete scenario, right? So yesterday I sent an SMS to my student Ido and asked him, are you excited for my talk at MSR? And so maybe Ido started typing a response. It's going to be, okay. And then at that point, the phone started to suggest a couple of different candidate completions. It's going to be terrible. It's going to be exciting. It's going to be tomorrow. Okay. So the question is, how does the phone know what to suggest? And of course, the answer is that Ido is not the only person typing into his phone. Lots of people are sending SMS all the time. And if we had access to the collected set of all the SMS that people are sending, we could just mine this data to train a model that then predicts what good completions might be. Okay, so this is exactly the kind of scenario that federated analytics deals with, right? So we have lots of devices. Each device has some local information, for instance, the SMS that the user has typed into that device. And the goal is to answer some questions about this data in the aggregate, right? So all the data collected together. For instance, how likely is each candidate completion for this particular sentence? And so the application that I sketched here just now is a real one, right? So this is what Apple is doing in iOS. There are lots of others, like for instance, to just mention one more, there are ways to collect statistics into homepages in Google's Chrome browser. Now, the thing that I couldn't represent on the slide, but that's really true in practice, is that there could be lots of users, right? Not just a few. And so if you think of the iOS deployment, Apple has about 1.5 billion active devices, and the people who are listening right now know about all the large deployments, right? And so in general, we have to expect millions or even billions of users in these systems. Now, how could we do this? And one way to do it, of course, would be to ask all the users to upload their data into a central place, right, which I'm going to call the aggregator, right? For instance, it's a data center that's operated by Apple or Microsoft. And then the analyst could just, send a query to this data center, and the data center could run some normal, data mining system to give the answer, right? So that's nice, that works, right? And then, once we have the final model trained on this data, we could download it back into the devices that could then make the predictions, right? So it works, but is this a good idea? And the obvious challenge is privacy, right? So this is a huge issue because the data that people are sending in SMS can be very sensitive, right? So just to give you a quick indication, like, this is XKCD captured this very nicely, where somebody's typing "long live the revolution," our next meeting will be at, right? And if that point you get a completion from other people, right, then you know where the revolutionaries are. Okay? So this can be very sensitive data, so we really need strong privacy protections. But the good thing is that there are actually techniques out there that can help us, right? And so differential privacy is becoming very popular as one answer to this problem, right? And so what it would do, like if we apply differential privacy to this problem, is it would take the model that was produced at the end, and it would sort of sanitize it, if you will, right? So it's safe to release, right? And that point, you can give it back to the users, and you get good guarantees that the users can sort of reverse engineer the model and tell what other users have been typing. And so this is well in its way to become the gold standard for this kind of application. It's widely used in practice. So Google, Apple, Uber have deployments, and the US Census even has been using it for the most recent census, right? So it's an established technique. And so not everybody in this on this talk will be familiar with differential privacy. So I want to tell you at least a little bit about how it works. But the thing is, there's a huge literature out there with lots and lots of subtle mathematical background, and I can't hope to cover all of this in this talk. So what I'm going to do is I'm going to give you the 2-minute version. Okay. So what is the 2-minute version? Well, the first thing is that differential privacy doesn't allow you to ask just any question, right? For instance, if the analyst asks, what did Andreas type just now? But that's not OK to release, right? Because it's very sensitive. Instead, the only thing that you can ask is queries with a limited sensitivity, right? And what I mean by that is that the data from a single user can make at most a small kind of bounded difference in the answer that you're getting, right? And so examples of that are counts or clipped sums, right? So if I ask the question like, how many users are typed interesting, right? Then that's the kind of query that we can answer because, if you leave out my data, then the count can decrease by at most 1, right? So that's the first part. The second part is that you're not allowed to give precise answers, right? So instead, you have to add a little bit of carefully chosen random noise to the responses, right? So you're not allowed to say there were 3,283 users who typed that word. You can say something like there were 3,278 plus minus 10. And it's a little bit more complicated than that. So the noise is usually drawn from a distribution like plus, but not much more complicated. And then the final thing is, there's a privacy parameter. There's sort of a knob we can turn to control how private we want things to be. And so, it's called epsilon, and smaller epsilons mean more private, right? But also that the price to pay is that there's going to be more noise in your responses, okay? And so these privacy parameters compose, right? So if I have 2 queries with 2 different privacy parameters, epsilon1 and epsilon2, then what is sort of the impact of asking them both, right? And the answer is we can just add up those privacy parameters and to get the cost of the combination of these queries. And so what that gives us a way to do is that we can define sort of a privacy budget. We can say, well, we're willing to answer about 14 units worth of private questions, right? And then we can just keep asking, and the cost of each query is deducted from this budget until it expires. Okay, so that's all I want to say about differential privacy, and that's all that you really need to know for this talk. All right, so differential privacy is great, right? But is it solving the entire problem, right? And the answer, no. Right? So we still need to have quite a bit of trust in the aggregator, right? So because the aggregator still sees the information in the clear that the users are uploading to it. Okay, so why is this bad? Well, the users might not like it because they might be worried that the aggregator might abuse their data or sell it to third parties or do some other nefarious thing with it. But the aggregators themselves might not like it either, right? Because having a huge treasure trove of data, like data from billions of users, is going to make them a prime target for adversaries who want to hack into their systems and steal this data, right? And so that exposes them to liability and so on and so forth, right? So even the aggregators might not be happy about having this data in the clear. Okay. So the question that we wanted to ask in this work is, can we work with an untrusted aggregator, right? So can we avoid having to give that aggregator this data in the clear? Okay. And so one way that you might think of doing this is you might apply differential privacy to the inputs instead. And this is, in fact, one technique that has been explored in earlier work. It's called local differential privacy. And so what that does is basically just add the noise instead of the answer. It adds it to the individual uploads. Okay, and so rather than uploading 1 or 0, we might upload something like 0.7 plus minus 1. Okay, and so this is good because now the aggregator can safely look at this data, right? So it doesn't really reveal what my specific input was. It could be 0 or 1. Right? But the price to pay is that now we have a lot more noise in the system, right? So all this noise will add up, and now our answer will be a lot less precise. And this is, how much noise is this? Well, it's enough that sort of some players have expressed question with this approach, right? So there's a paper, for instance, by Google, at SP 2017, that says, look, the magnitude of this noise with this technique is so large that even a signal from 1 million devices can easily be drowned out. Okay. And then the other way that you could deal with this is you could adjust a privacy parameter like a knob, right? So remember there was this knob called epsilon that they can turn to control how private things should be. And a common recommendation for this knob is to use a setting like epsilon equals 1, right? So that seems like a common recommendation from papers about differential privacy. But what Apple did was, they actually turned that knob all the way up to 14, right? And not just to 14, so 16, I think. They refresh the budget every single day, right? So now you're getting a lot more information out of the system, right? Because the privacy guarantee is turned so low, right? But the users are also getting a very little protection to the point where like the privacy guarantee is not very strong. Okay. So there's other sort of solutions that people have thought about, right? But among these 3 goals that I've mentioned, right? So we want to have an aggregator that we don't have to trust, right? We want to have accurate answers to our queries, and we want to be able to scale to millions or billions of users. Out of these 3 goals, they tend to achieve only 2, or at most 2, right? So local differential privacy can give you the single aggregator and scalability, but it doesn't give you good accuracy. Right? There are other approaches that rely on crypto. That's fancy things like fully homomorphic encryption, multi-party computation, threshold crypto, and so on. And they can give you high accuracy. They also give you the ability to not trust the aggregator, but there you can scale to maybe like 100 or maybe like 1,000 users, but you're not going to go anywhere near like 1 billion users with this approach, at least the ones that I've seen. And then the final approach is to add more trusted parties. Like, for instance, you can bring in the EFF, right? And they can also run a data center. And together, EFF and Microsoft can, give better privacy guarantees. And that also works, but in practice, it could be difficult to make that happen. Okay. So what we wanted to do in this line of work was to provide an option for federated analytics that has all these 3 properties, right? So we don't have to trust the aggregator or some kind of fancy hardware like trusted platforms. We want to have good scalability, right? So going up to something like 1.5 billion devices, and we want to have good accuracy, right? And it should be ideally as good as with this original approach where we just give all the data directly to the aggregator, right? And then on top of that, we want to be deployable, right? So it can't be too expensive, and we want to be able to have a manageable privacy budget, like we don't want to run out of budget on day one. Okay, and so the question is, can we do this? And when we started to work, there wasn't really much on the sort of the map of possible solutions, right? It was pretty much blank, right? Mostly because of the scalability, right? So there are lots of techniques out there, but they really can't reach the sort of million or billion device level, okay? And so that's what really, I think, forced companies like Apple or Google to make this trade-off, right? So to either live with a lot of noise, right, and that sort of limits what you can do, or to adjust the privacy parameter to a level where it's not as strong for the users. Okay, so can we give a better solution? Okay, and so in the rest of this talk, I'm going to sort of tell the story in 3 chapters, right? So the first chapter is about can we do it at all? Right? The second chapter is going to be about can we do it for more things? And the third, very brief chapter is going to be about something that we're currently working on, which is to do it for graph-shaped data. Okay, so this first chapter is going to be about a paper that we published in SOSP 2019. All right, and so what is the thing that we're willing to assume in the system, right? So we want to support fully malicious users and fully malicious aggregators. Just like we don't want to assume that the users have some particular goal or that the aggregator is good or something, right? So we want to be safe, right? But in this space where people make this assumption about fully malicious, a lot of work is very pessimistic in the sense that they assume that up to 1/3 of the users or can be malicious, right? And that's just a lot, right? So if you make that assumption, it's really hard to do something, and even if you can do it, right, it's going to be very expensive. But our argument is, well, in reality, when you have 1 billion users, it's not, maybe it's not, very common that 1/3 of them are malicious, right? So instead, we use a slightly different model where we make these 2 assumptions that we call OB and MC, right? So OB means that the aggregator is only occasionally Byzantine, right? So all malicious, right? So they might be, right? For instance, maybe a disgruntled employee, hijacks the system and breaks it in some way, right? For short periods until they're discovered, right? But they're not going to be malicious all the time, and particularly not at the beginning, where they can sort of roll out a malicious operating system to all the devices. And then the other assumption is that the users are mostly correct, and by that I mean, maybe 3% or so would be malicious at any given time, and 3% at this scale is still a lot, right? So it's something like 45 million nodes, and that's still sort of larger than most of the botnets that I can think of right now. Okay, so that's still a fairly good assumption. The other things, we make some more assumptions, and the most prominent ones are that the aggregator can help a little bit, right? So they're going to have a data center with some resources that they can use to help this computation, even if they are not trusted. And that each device has some kind of key pair, like the iOS devices do. Okay, so we wanted to see what we can do, and we wanted to start with like a real problem, right? So we took a query, like an analytics task that was from Apple's actual deployment, right? And so what Apple turns out to need is something called a count mean sketch. So what does that do? Right, so remember, the goal is to train a model on possible completions, like for predictive typing, right? And so what this does is basically, like, suppose you have some users and 100 of them typed Honeycrisp, 58 Granny Smith, and 27 Dr. Oldborg. These are all types of apples. Okay. Then what the count mean sketch would do is it would basically have a fixed number of bins and would hash all these words to a fixed number of these bins, like for instance 3. And then it would add up all the sort of numbers, like how often people have typed these things in a given bin, right? And then if you afterwards wanted to know sort of an estimate of how often somebody has typed this particular word that you're interested in, you would just take all the bins that it hashes to, and you would average the counts from these bins. Right? So this is a standard technique. and Apple wanted to use this. For all purposes, what this means is that what we're going to be computing is lots of counts, essentially, right? So we're going to be counting the number of users that have words, typed words that are in some particular bin. Okay. And if you're curious, why counts, this is not a coincidence. I'm going to talk more about why this is a common thing later on. Okay. The other thing to keep in mind is that these queries are going to be repeated regularly. And that's because word usage keeps changing. Like, for instance, before January the 6th, people didn't type the word insurrection all that much. And after that day, or on that day in particular, they typed it quite a bit. Right? So word usage does change. And so we need to rerun these training tasks once in a while to make sure that the prediction stays accurate. Okay, so here's a first sort of idea, what we could do. Right? So we could use, so what we want to do is we want to add noise only once, right? So we don't want to noise the individual contributions, we just want to noise the answer. Right? But we want the aggregator not be able to see the individual data items that the users upload. So what we could do is we could use additively homomorphic encryption. Right? So what that gives us a way to do is we just add up ciphertexts to get the ciphertext that encrypts the sum. Right? And it's much cheaper than fully homomorphic crypto, especially at this scale. Right? So this is a practical approach. Right? And so what we would then do is basically like all the users could encrypt their information with a public key and upload the ciphertext to the aggregator. And then the aggregator could add them up using this homomorphism and get an encrypted sum. And then the aggregator could decrypt only the sum, maybe after adding in some noise. And then they would not learn what the individual inputs were. Okay, so that's nice. But the obvious problem is, who should have the private key for this crypto system? Right? So if the aggregator can decrypt the final sum, nothing prevents a malicious aggregator or a curious aggregator from decrypting also the individual inputs. Right? And so that's something that we wanted to prevent. So how can we sort of evolve this proposal to make that a little bit more robust? Okay. And so the next idea that we added in our system was the sortition and sharding. Right. So instead of giving the aggregator the key, we elect a small committee of user devices. Okay. So there's a small number of devices, maybe imagine like 3 or 4 dozen, right? And these devices together are going to be the committee, and these devices are going to keep shares of the private key. Right, so each device individually has only a small bit, right? So they all need to combine both of those shares together to be able to decrypt anything. Okay, and we can use multi-party computation to generate these shares. And then what we can do is we can have the aggregator at the end, take this one final ciphertext, which is the sum, send that to the committee, and then the committee decrypts that and sends the result back to the aggregator. Right, so the aggregator can really do only one decryption. Okay. Now, this is not as easy as it sounds, and one of the reasons is that the devices have to be chosen carefully, right? Because if the aggregator were malicious, then the aggregator would want to bias the committee towards its confederates, right? So devices that it controls, so that it sort of works with, okay? So we really need to have an unbiased sample, right? So if you could have an unbiased sample of devices, then the fraction of malicious devices on the committee should be sort of roughly the fraction of malicious devices in the overall device population. And since that was low, like we sort of have some hope of doing this. Okay, and so how do we do such an unbiased sample? And so here we use something that's inspired by the sortition technique in the algorithm paper a while ago. Okay, so how does that work? And but at least sort of give you a glimpse of how that works, and just so you can see what the technology underneath is. Okay, so there's some kind of random bits that the system has to maintain for each round. And so the computation proceeds in rounds. So maybe like every day we ask a question of the system, and every day we want to produce an answer. And each of these days we have some of these random bits. Okay, say it's 89. And so then each device takes its private key. So remember, we assumed that the devices had these key pairs, and it signs a triple, BI, I0, where BI is the random bits, and I is the device number, and 0 is just a constant. Okay. And then it hashes the signature and then it arrives at some kind of number, which I'm showing in green. Okay, and these are for all purposes pretty random. Okay, as long as these random bits are random. And then we're just going to put on the committee the devices that have the lowest numbers. And the good thing about this approach is that we can verify whether a given device should be in the committee. Whereas if I claim that I've been elected to a committee, you don't have to believe me. You can actually take sort of this computation that I can publish, right? And you can verify using my public key, right? So you don't have to know my private key for this, right? So it's nice that we can verify who should be in the committee, okay? And so then where do these random bits come from? Well, we do the same thing essentially once again, using a different constant as in this third element of the triple, right? And then
Hey guys, it seems like we lost Andreas. Let's give him a
couple. Nope, I'm back. I'm back.
Here we are.
I don't know what happened there. Okay, so good. So this is the sortition protocol. Now, the question is, what can the adversaries still do? And there's still a couple of things that we have to be careful about. The first is that adversaries could upload bad data, right? For instance, I could hack my device, with a billion devices, that's always possible. And I could just pretend that I typed the word foo like 100 million times, right? And that would render the final answer useless, right? Because it's just going to be some huge number. Right? What we can do for this is we can ask the devices to clip their numbers to some reasonable range, right? Say between 0 and how often can I type a word, maybe 100, right? And then we can include a zero-knowledge proof from each device to show that the encrypted data is in that valid range. Okay, and so then the aggregator can verify that and make sure that all these ciphertexts indeed encode like a valid contribution. And then the other thing that we have to be careful about is that the aggregator could compute the sum incorrectly, right? For instance, instead of summing up all the data from all the devices, the aggregator could just take the data from my device and multiply it with a billion, right? And then ask the committee to decrypt that. And the problem is that now the committee is going to add in some noise, right? So proportional to, what you need to hide one user's data, right? And given to this how large this number is, I multiplied it by a billion, right? It's just going to be completely drowned out. So now you have my data in the clear. Okay. So what we need is some way to verify that the aggregator has computed the sum correctly. Okay. So every ciphertext should be included exactly once. So how do we do this? And the answer is the aggregator can compute a summation tree, right? So all these encrypted numbers, it can just sort of encrypt pairs of the sum up pairs of them, get some sums, then add up some sums, so get bigger sums, right, and so on until it gets the sum at the root. And then we can have the devices each check a couple of these triples, right? So a couple of different points in this tree to see whether each individual addition has been done correctly, right? And then at the end, if all goes well, we can give the top to the committee. But if the dishonest aggregator modifies something in this tree, right? So maybe multiplies my data by 100 or so, right? Then hopefully one of the devices with high probability is going to catch that, raise the alarm, and then the committee will refuse to decrypt the final the number at the top. Okay. Right. So there's one more thing that I have to talk about, which has to do with the fact that so we have this privacy budget, and what if that budget runs out? Right? So we do something every day, right? So we have to decrypt, we have to deduct the cost of the queries every day. Right, and then very soon, no matter what the budget is, right, it's going to be exhausted. Right, so what can we do about that? And so the thing that helps us here is that the data in this case doesn't really change all that quickly, right? So for instance, word usage, right? So almost all the time people don't type insurrection all that much, right? So I'm showing you some data here from Google Trends, but sometimes the number goes up quite a bit. Okay, and so what that means is that we usually have a pretty good guess as to what the answer should be, right? Which is simply yesterday's number, right? So it just, if the number yesterday was 10, we can just say like, well, I guess today the number is still 10, and it usually that works. Okay. So what we can then do is we can basically go to the system every day and say, well, is the number still 1? The system says, yep. And then we go again and we say, is the number still 1? The system says, yep. And then sometimes, but not too often, the system will come back and say, nope, it's not 100, it's not 1 anymore. Now it's 100. Okay. And there is a technique from the theory literature called the sparse-vector technique that essentially allows you to charge your budget only when the answer actually changes, right? So when you guess wrong, right? And so the reason why that works is simply that when you had this guess and the guess was right, you didn't really learn anything from the actual, actually very little from the actual answer, right? But if the guess was wrong, then and only then do you actually learn quite a bit, and you have to charge the budget. Okay, so we can take this technique and apply it here. Right, and that gets us sort of, and some other things like I'm not going to talk about, gets you this overall first system. Okay? So to just quickly run through it again, right? So how does this work? So we select a small number of devices, think of like 30 or 40, right? That are going to be in the committee. The committee makes a key pair for this encryption scheme using multi-party computation. That works because there are not too many of them. And then it gives the public key to the aggregator, and the aggregator just gives it to the users, who each upload their data as a ciphertext, so they encrypt their data with this public key. The aggregator then sums up the data, and it's all ciphertext, so you can see what it is. Users verify that sum is correct, and then the aggregator just gives that encrypted sum and its guess, which could be yesterday's number, to this committee. And the committee, if the guess is correct, it just says it's correct. And if it's not correct, it deducts the cost of the query from the privacy budget and returns the actual answer. Okay, so this is roughly how the system works. So what does it give you? Well, it gives you 4 guarantees that I'm going to state informally here. The first is privacy, right? So the user's data can't be learned by the aggregator or by other users. You get correctness, right? So basically the answer to the query will be the actual answer modulo noise. You get liveness, meaning that queries are being answered while you still have budget left. And you get this property called indemnification, where basically if a device is malicious, it can't pretend that a good aggregator has done something bad, which would be a concern. Okay, and so we have proofs of these things and more formal statements that are in our technical report. Okay, so let's have a quick look and see how well that works. Okay, so we have lots of questions that we asked, and we have lots of results to answer them. And so here I'm going to cherry pick a couple just to sort of give you a flavor of what that looks like. All right, so let's first have a look at what we did to answer these questions. And this is harder than you might think, because in my lab we don't have a billion devices lying around, so we had to do something to help with the experiments. And what we did was, like, the client side you can measure directly, right? Because what one client does doesn't really depend on what the other clients do, right? But for the aggregator, we basically benchmark the individual pieces, and then we extrapolated the cost that an aggregator would have if it did have a billion devices. Okay. All right, so let's have a look and see how expensive this kind of thing is. Right, so we look at traffic and computation. I'm going to show you like several different system sizes, including the one that we sort of target in the middle. Right, I'm going to show you traffic and computation. So here are the results that we are getting. And so if you just squint and look at these graphs, you can see that the cost doesn't really depend very much on the system scale, right? Because what the user does, there's a small logarithmic factor, but what the user does is pretty much independent of how large the system is, right? And in absolute terms, the cost is not that bad, right? So the users upload something like 1.2 megabytes because these ciphertexts are pretty large, right? And the computation is roughly 60 seconds. And I know these are devices with batteries, well, this is not completely trivial, but you could do it at night while the device is plugged in. Okay, and now this is for the common case, which is almost all the users which are not on the committee. If you are the committee, which is 10 users out of the 1.3 billion, right, then you have to do more work. Okay. Now, what about the aggregator? Like, what does the aggregator have to do? And so here things get a little bit more expensive, right? So you can see here that first of all, scalability numbers, right? So how does the cost depend on the size of the system, right? You can see here, it's pretty much linear. Like, once again, there are small logarithmic factors, but it's mostly linear, right? And you can see that so it scales very well. Right? So you can actually do this at something like 1 billion devices, right? But in absolute terms, the numbers are significant, right? So you need something like 45 cores if you want to be done within an hour or so of at the aggregator side, and you need to send about 1.4 like 1,450 terabytes of data. Now that sounds like a lot, right? But if you think about it, like it's the number is big just simply because the system is big, right? So if you have 1.3 billion devices, right, then that corresponds roughly to about 2 out of 3 downloading a typical web page, right? And so, like, if you have a really big infrastructure with for the deployment that size, that cost actually should be fairly manageable. Okay, and then the final question is the one about the budget, right? So remember, I said, look, in a system like this, you can't run out of your budget quickly, right? And so how do we do on that front? And so for this, we compared our system to sort of an Apple-like system that uses global differential privacy. And we're plotting the recommended sort of privacy budget of 1 here on one axis, right? And if you look at sort of the iOS-like system, right, so you can see that it runs out of privacy budget pretty quickly, right, after about 3 months. But our system would last much longer, right? Because the cost, because of the sparse-vector technique, is much smaller, right? So it can last about 10 years, right? Which is pretty good for a system this size. And so we're extending the lifetime of the system by about a factor of 40. Okay, and so what that means is now we get very good privacy guarantees, right? So we have sort of the recommended setting for the privacy parameter, but we're not giving up accuracy, right? So remember, we're not having this huge amount of noise that can drown out like a million devices, right? We can actually answer queries fairly precisely with this approach. Okay, so now let's move on a little bit to the next piece, which is about making the system a little bit more general. Okay, so let's assume a different scenario. Let's say we have a retailer, I think Walmart or somebody, right, who wants to build some additional shipping centers. And so they wanted to say, decide where they should go, right? They want to be close to the users. And let's assume that the users have some app, right, that knows what a user is, right? And so what we could do, like if you had all this data, you could simply run something like k-means or something, like a data analytics algorithm to decide, what positions would be close to all of these users. Okay. So that sounds like a job for federated analytics, right? Just very similar to what I've talked about earlier. But the problem is that the system that I've described, but this Honeycrisp system, was very specific, right? The only thing that it could do was these cant mean sketches, right? And so that is sort of not the only thing, obviously, that people want to ask, right? So there are lots and lots of queries that you could imagine people wanting to to ask of such a system, right? I'm listing some of them here on the slide, right? And we just really can only do one of them, right? So that's frustrating, right? And so it may seem as if we had to sit down and for every single new query that we might want to ask of the system, we'd have to build a completely new design for the system. And that seems pretty scary. Okay. But is it really that bad? Okay. And so we thought about this and we realized that while these queries, these differentially private queries, may look very different at first glance, they actually have a lot in common, right? So it's just not hard, it's not easy to see. Right? And so to give you an intuition for why that might be, I'm going to show you an example, which is the k-means code. So how you would write down this k-means query in our system. And so there's no need to look at the details, right? I'm going to show you the structure of this. Okay. So when you squint a little bit and look at this query, you'll see that there are some pieces that are completely local to each node, right? So for instance, the node looks at its local information and decides which cluster center it's currently closest, or like finds out what its current location is. So these are all node local operations. Okay. Then there are some pieces where things are being summed up. Aha, right? So this is something that we can do, right? We know that from Honeycrisp that we can sum up things at least, right? And then there's some post-processing, right? So the system has these sums and it does some, for instance, moves the cluster centers to a new location. That's all of these things, but that's sort of done, can be done in a centralized position, okay? And so, why is this, right? So why is that is this surprising structure inside these queries? And I think it's probably a natural consequence of these differentially private mechanisms, right? So remember that the demand from the very first slides was that we needed queries that have a slow sensitivity, right? So we need something that doesn't change very much when you remove the data from one particular user, right? And these sums and counts, these are just very natural functions that have that property. Okay, and so the problem now is, well, there's these sums hiding a lot of these queries, but the analyst might not know how to reformulate that query to expose those sums, right? And so we built a system called Orchard that can help with this. Okay, so Orchard, basically the analyst goes to Orchard and they write down their query in whatever way seems natural, right? So as if the data were collected in a single place, right? And then Orchard takes the query and transforms it into a distributed protocol, right? That can answer this query with differential privacy, right? Without collecting it in a single place, okay? And so it's using internally a primitive that feels a little bit like Honeycrisp, and I'm going to call that BMCS for reasons I'm going to explain in a moment. All right, so what we're going to do is we're going to take this query, we're going to break it into pieces, right? The first piece is going to be running locally on each user device. The second piece is going to be running at the committee, right? For instance, summing and noising. And the final piece is going to be running at the aggregator, okay? So how do we sort of come up with a primitive that all of these queries can use? And to answer that, we sort of thought about what it is that Honeycrisp really is doing under the hood, right? So it does it extracts the word frequencies from the words that you type in your SMS application. Then it clips these frequencies to a certain range, right? So remember, we have to prevent adversaries from lying about how often they typed. And then it sums up the clip frequencies. Right? So morally, what we're doing is we're mapping some local data to data we can upload. We're clipping this data to a certain range, and we're summing all the clip data items from all the devices. And it turns out that for many queries, you need something that you didn't need for the k-means query, which is that you might have to do multiple rounds. Right? For instance, in k-means, right, you have to you compute some initial cluster centers, and then you have to do another round and sort of move them a little bit based on what the initial centers were, right? And so for that, you might have to take some data from the previous round and broadcast it to all the devices for the next round, right? So there's a broadcast step here too, right? So we need to broadcast, map, clip, and sum, hence this BMCS primitive. Okay, and so the program can run this multiple times, right? For instance, if k-means has multiple iterations, then we can just run that, for each iteration a couple of times. Okay, so now, don't look at the details of the slide, right? But the idea is, well, we're given this query and we need to transform it into one that we can run in a distributed fashion, right? So how do we do this? And so at a high level, what we do in the system is we transform the query into a data flow graph, okay, with the dependency edges, right? And then we identify these you can already see this in the illustration, right? These map, clip, sum steps, right? Which we replace these parts with this BMCS operator internally, right? And then we do some optimizations. And this turns out to be really important, right? Because this BMCS primitive, as you've seen previously, like it has a cost, right? So you want to do this not more than we have to, right? And if you look at this, right, so you can see this sort of SIMD structure. Like we have the same data, but we do multiple things with it, right? And so this kind of structure we can actually exploit with optimizations, just like in a standard compiler, pretty much, right? To replace it with, for instance, a parallel sum and flip operation. So we can just run multiple instances or multiple invocations of this protocol in parallel. Okay, so let's have a quick look and see how well that works, right? And so again, like we had lots of questions, and I'm going to cherry pick a couple of answers to show you in this talk, right? Primarily, like how general is it and how expensive this turns out to be. And so, how general is something like this? And so to answer that question, we just went out and looked at the whole literature for differentially private analytics, and we looked for different kinds of queries, right? For instance, like lots of papers look at, CDFs or, answering range queries and so on. And so if we had multiple papers that answer roughly the same kind of query, like we counted that only once, right? And so then at the end, we ended up with a set of structurally very different queries. Right? So we had these 17 different kinds of queries. And then we just sort of went out and looked how many queries Honeycrisp could support and how many queries Orchard could support. And so for Honeycrisp, the picture looks pretty bleak, right? So we've seen that before. It can really only support one query, which is these cant sketches. Right? But for Orchard, things look very good. Okay, and so we can actually do 14 out of the 17 queries. And so you might ask, why not the other 3? And that, the answer depends a little bit, right? So the for distress, right? So this is one of the earlier works that works on graphs, right? We don't support graph shaped data. We just support like per device data. Okay. For IDC is sort of like a template algorithm where like you have an oracle function U, and you have to when you want to make a good choice for this U, you need something that's more complicated or you currently support, right? And for Pate, you have to do some training on the unnoised data, which we can't do in this setting. Okay, so but overall the picture is very promising, right? So for most of these queries, we can actually support them in Orchard, even without sort of the analysts having to understand exactly how to do them or how to expose these internal sums that we happen to be able to do. Okay, oops. All right. Okay, so now let's talk about cost, right? So like how expensive is this? And so again, like we did similar experiments as for Honeycrisp, right? So we measured the user the part of it, right? Because that's independent of the rest of the system, right? And I'm showing you here the cost for all these different queries that we can support. And for comparison, I'm going to show you, like I'm showing you here on the left, the cost of Honeycrisp's single cant sketch query, right? And you can see, overall, right? Some of the queries are more expensive, like mainly because they need have more complicated data or need multiple rounds, right? But in general, right, so the ballpark is pretty much the same as Honeycrisp's, right? So the cost is still on the order of a couple of megabytes per user device, and the computation is still on the order of like a minute's worth of computation per device. Okay, so it's still sort of very, very feasible. It seems very feasible to run this on normal user devices. Okay, so I'm going to very briefly tell you about where we're currently going with this work and what is sort of the next step. And the next step has to do with graphs, right? So we've seen with the COVID situation that it makes a lot of sense to sort of have solutions for dealing with pandemics. Okay, and so for COVID we had this, or still have these contact tracing apps where basically your phone broadcasts Bluetooth beacons to nearby phones, and then if somebody who you've been close to is later diagnosed with COVID. All right, so you get these edges here, like people have been close to each other. And if somebody is diagnosed with COVID later, your phone can alert you. It can say, well, you've been exposed to the virus because you've been close to somebody. I'm not going to tell you who it is, right? Who was later diagnosed. Okay, and so if you have a situation like this again, God forbid, right? But we want to be able to. It would be nice to use this kind of information to do more, right? So right now it just does exposure notifications, right? But it'd be nice to be able to answer questions as well, right, about the disease. For instance, where do infections usually happen, right? What kind of role do super spreaders play, right? What kinds of behaviors are particularly risky? Like, where are you most likely to become infected, right? Do external conditions matter? Like, for instance, humidity, like temperature or something like this. And these are all tricky questions. We've been talking with medical experts at the hospital of the University of Pennsylvania, and right now it's just very, very difficult to get studies going about this. right? Particularly large-scale studies. Right? And so there's this data right there, right? So your phone knows where you've been, your phone knows who you've been close to, right? So in principle, we could help the medical researchers answer all these questions using some of this data, right? But now we obviously have privacy concerns again, right? So we need a system with very, very good privacy guarantees, right? And we need one that scales, right? Now here it turns out to be even more challenging than in Orcho's case, because the aggregator can't really process the data on its own at all, right? So like if you imagine that you have to do some kind of graph computations, like not just summing up things, that's not enough, right? Some kind of graph computations on this data, right? Additively homomorphic crypto is not going to cut it, but so you need fully homomorphic crypto. And now imagine if you've worked on this before, imagine operating on a 1.3 billion times 1.3 billion adjacency matrix with this, right? It's not going to, with current technology, it doesn't seem feasible at all, right? Now, what we can do, there are all things we can do though, right? So one of them is we can restructure the computation again, right? So to help with the overhead into maybe two pieces, right? So one piece could be a local computation, where each device talks to the devices it's been close to in some way, and to figure out has anybody nearby been infected? So the local answer to some of these questions, right? So where have I been when I was infected? For instance, was I on the subway? Was I in a restaurant, right? And then a second step could be a global aggregation, where we just sort of take all the data from all the individual users' neighborhoods and build a global picture for the analyst to see, right? So that something that we're currently working on, right? So I don't have a final answer for you yet, right? But the big challenge, of course, is again, we need to do this very privately, because this data is incredibly sensitive, like where I've been, right? My movement patterns, what I've done, right? So the only way we can get people to participate in a system like this is to give them very good assurances that the data is going to be private, right? And so we need to protect the communication. We need to protect obviously the data itself, right? So it has to be very strong. Okay. So where does this leave us, right? So if you think about it, right, when we started the project, right, the map of solutions was pretty much blank, right? So it was really not I'm not aware of any solutions that could scale really to 1.5 billion devices and can give good accuracy and have only a single untrusted aggregator, right? Now we've made some progress, right? So we've conquered one little island here for the CMS Convene sketch queries. Then we made a little bit more progress, right, with Orchard, where we can do quite a few sort of queries that can be rewritten in this way. And right now we're still taking the next step and looking at graph-shaped data, right? But overall, the map is still very, very sparse, right? So there's lots of things that we'd like to do that we currently cannot do, right? Okay, so to summarize what I've talked about, right? So the goal that we have in this work is to support massive scale federated analytics. Right? That's why I had the at scale of my title slide was in red, right? For this reason, right? We want to have billions of users. Okay, and so this is not a made up application, right? So these systems exist today, right? So they're running on my phone right now, right? In my browser right now, and the data is incredibly sensitive, right? So we really need strong, good privacy guarantees. And even differential privacy, we need to have a deployment with strong privacy parameters. Okay. Now, differential privacy helps us, right? But it solves only part of the problem, right? We need to, the published result is safe, but the aggregator that computes this result is not. It has to be trusted, and that's the thing that we want to avoid. Okay. And so, not many options available, but we were able to find a couple, right? So we have this Honeycrisp system that can do Convene sketches. We have the Orchard system that can generalize this a little bit. And right now we're working on a system that can do graph-shaped data, and hopefully they'll be able to push it even more. Right, that's all we have. That's all I have. Thank you so much for listening. And if you have any questions, I'd be happy to answer them.
Thanks so much. That was a super interesting talk. And we have a few questions. So I'm going to go through chat and just ask you the questions people have asked before, and I have a few myself. So the first one is a liveness question. They're asking, are the questions explicitly or implicitly denied when you return queries? And what information does the denial itself leak?
Right. So the technology, right, this sparse-vector technique is from the differential privacy literature, right? So the answer that you're getting is in itself differentially private, right? So even if you have the correct guess, right, the system might have to say no with a small probability, right, and vice versa. Okay, so it's not a perfect answer, right? But the denial, so basically modulo that, right, the denial just says your guess was wrong, right? Even if sometimes the system might have to say that when the guess was correct, actually, right? So that is not a long story short, that is not a vulnerability, right? So this is a technology from the actual differential privacy literature that we did not invent, right? And it's been proven to be differentially private.
Mm-hmm. The next question we have is, can the system handle malicious participants, or are the participants trusted?
Right. So the let's see. Well, I can bring up my little slide there. So the threat model was that the system can. So the users, the users who own the devices, they can be malicious, right? So it's possible in our threat model that users will hack into their phones, will take complete control over the operating system and all the software in the phone. It will send and receive any, like, basically control what data they can send and receive, right? So, but the assumption is that there are not too many of those, right? So that is the big assumption we make. Like maybe like 45 million devices, that's 3% of the total, right? Not more, right? If like a majority of the devices were fully malicious, right, it would be much harder to do something if you also insist on efficiency, right? And so that's why we make that assumption. But yes, the devices can be fully malicious, a few of them. Even the aggregator can be malicious, just not all the time.
Mm-hmm. So I'm going to use the fact that you have the slide up and ask my own question. So my question is more on exactly this slide, which is, how do these assumptions that you laid out here factor into the proofs that you have and like how the system works? Especially for me, my curiosity was, how do you use this assumption that the aggregator can just occasionally be Byzantine as opposed to all, like having a consistency assumption?
Right. So one of the there's a couple of points where we need it, but one of them is that so imagine Apple is malicious all the time, right? Then the one thing I can do is they could just sort of compromise iOS and make iOS take all your data and upload it to Apple, right, without encryption, right? So we need a way to make sure that at least the software on the non-compromised devices is sort of doing a good thing. And so if the aggregator has control over the platform that's used to run this, which is true in Apple's case, right, then we need them to at least sort of not break the software on all devices, because that would be a correlated failure, right? So then all the devices would be malicious, quote unquote, right? And then we couldn't do anything.
I see.
Yeah. So the other assumption is about the fraction it has to do mostly with the committee, right? So that we use that, for instance, to prove that the committee, it doesn't have too many malicious devices in it. And if that were the case, then they could leak the private key for the encryption scheme, and then all bets would be off because the aggregator could decrypt all the user data.
Got it. Thanks. So the next question we have is a high-level question. They ask, in general, real-world data tends to be highly compressible, both lossily and losslessly. What sort of data sets and queries will this work for, and where it won't? Are there any theoretical underpinnings to make us feel safer?
So there are two parts to this question. One is what is the theory that should make us feel like this system is safe to be trusted with our sensitive information? And the answer to that is the theory of differential privacy, right? So this is not something that we came up with. Like, it goes back to Cynthia at work, like way back at MSR. And there are lots of people have worked at it over many years. There's lots of this. It's very well understood. Lots of proofs, lots of deep math behind it. Right. So this is not a heuristic in any sense. Right. So it's widely accepted. Like, it's used by the US Census. Like, people understand it very well, I think, and that's the reason why at least I feel confident that you can trust the system, right? And that in combination with the cryptographic techniques, right? So there again, like, if you're willing to trust the hardness assumptions, like that people can factor large numbers and so on, right? That's a good foundation for trust, right, in this system, and that's where the trust comes from. Now, the other question I think was, like, how general is it? And so that's a hard question to answer, right? So like with Orchard right now, we can do things for queries that can be rewritten using the sums that we happen to be able to do, right? But the question is, like, how large is that space? And we have only this sort of informal study where we just looked at the literature and see what queries are out there. It's hard to characterize this better than that, right? But it's work in progress, right? So like we'll keep looking for queries we can support, and we'll keep looking for ways to answer those. But right now it looks pretty good, at least encouraging to me.
Thanks. So the next question is from Kevin Hessia. He's asking, he's saying, interesting talk. I have a general question on how you see the differences between federated analytics and federated learning, which runs models training on participants and only aggregates models. Can you shed more light on how federated analytics can support high-dimensional unstructured data, such as images and videos?
Right. I guess it's a federated learning, like, has a very specific meaning it's basically about machine learning tasks, right? You want to train a model, you want to learn something. But federated analytics is maybe a little bit more like has a sort of a broader meaning where like you have a query, not necessarily a machine learning query. It could just be like how many people have gotten COVID while they were in the subway or something, right? And then it can help you answer those queries. Can you repeat the second part of the question?
Yeah, so he says, can you shed more light on how federated analytics can support high-dimensional unstructured data, such as images and videos?
Right. So the question, so I guess the question has to do with, or the answer has to do with what the query exactly does, right? So if the query is something that can be factored neatly into per device computations and some kind of smallish global aggregation. And so like in federated learning, there's quite a few of these that have that property, but then there's hope that you can do it with the technology that you already have, right? For instance, oftentimes like with federated learning, like you want to aggregate these gradients that you've trained locally on the devices and then send it back using a broadcast to all the devices to be improved. But that's the kind of thing that you should be able to do, right? But there are other things like where you have a lot of interaction, like you have lots of huge matrices being sent around. And there, I think one of the limitations is just of overhead. Right? So if you had to ship around lots of data with fancy crypto systems and zero knowledge proofs, we'd have to think much harder about how to make that work with current technology and how to make that efficient. And I'm not saying it can't be done. It's just something that we haven't sort of figured out yet. And so if somebody has an interesting use case, right, so something that they really want to compute with strong privacy guarantees in a super large scale setting, then please come talk to me. I'd love to hear about it, and we'll see whether we can figure something out.
So the next question is also mine. So my question was, how is this, how would you see this in comparison with the type of work that, for example, Alejandro Rivero has done some work at Penn, where he does distributed optimization. Basically, you're distributing the computation itself across nodes, and you're passing parameters of the computation as opposed to data itself. So you're not passing around data, you're passing around, for example, your Lagrangians and things when you're doing the computation. So how is this different, and can you map this world to that world at all? And what's the relationship?
Yeah, so I think the answer is, so there's that sounds like a kind of a computation that's much more rich and complicated than the one that we're currently able to do. All right, so you have some kind of truly distributed protocol where nodes can send data to other nodes and so on. And so that's not something that I know right now how to do to make differentially private at this scale, right? But it's very much interesting, right? So like the question that I would have is like, can you give a specific use case, and can we think about what it would take to make that work in this setting? Right. So it's an interesting question. Like I said, like the map is pretty blank in that space.
Mm-hmm. So the last question we have, actually we have one more, but the other question we have is, do the algorithms using Orchard use up the privacy budget at different rates? Yeah, so they do. So that the privacy budget doesn't have to do so much with the way the query is executed, but rather with sort of the thing that the query computes. Right? So it depends on how sensitive the query is, like how much can a single user's data change the result, right? And that's a property of the query, not of how we provide it. And so that does differ between the queries. Some of them are more expensive because they're more sensitive, and some of them are less expensive. Mm-hmm. And so this one is the last question so far, which is, what are some known gaps between the theoretical aspects of differential privacy and what has been implemented by practitioners? So I'm not sure I fully understand I'm understanding the question correctly, but there's a very rich literature in differential privacy, and there are lots of cool things that people have proposed that hasn't necessarily made their way into actual practice. Right, and for lots of reasons, maybe it's too new. Maybe people sort of haven't really matched it with the right application yet. Maybe there are pieces that are missing, such as maybe the application itself is too large and we don't know how to do it at scale, and so on. So there's a lot of stuff out there, right? And there are lots of opportunities for somebody who has an application, a use case with privacy challenges to go and look at that literature and work maybe with systems people to make it happen in practice. So I think that was our last question. So thank you so much, Andreas, for being here. I think a lot of us have one-on-ones with you throughout today, so we're looking forward to that. And thank you again for the talk. It was awesome. Thanks again for having me. Thanks. So with that, we'll conclude this talk. Thanks, everybody, for joining us.